floor is yours.
Wonderful. Can you see my screen again, just to double check?
Yes, but now it's not in presentation mode.
Yeah. Right, so welcome back, and I'm now going to be talking about how to carry out 1D electrical resistivity surveys using a terameter and 1D cables. So I think the first thing to think about when we look at resistivity surveys is about the rock properties themselves and the sorts of measurements that we're looking to obtain in terms of the apparent resistivities of these materials. So if we look at, for example, clays, we find their resistivity to be low. They're very conductive. So we're looking at in the range of between 5 to 10 ohms per meter resistivity. If we look at sand and gravels, this is much more dependent on the water within those sands and gravels. So saline water might also have very low resistivity because of the salts in the water conducting that electricity. Fresh water in general has a resistivity within a sand and gravel has a resistivity of between 10 to 1,000 ohms per meter. So that would be depend on the water storage within the materials as well. And then a dry rock, sand and gravel, would have very high resistivity indeed because there's very little conductivity going on. Igneous rocks, metamorphic rocks, also depend quite a large range of different resistivities based on their weathering profiles. With obviously the more they've been weathered, the more conductive they are. So here's a different table showing similar sorts of resistivity ranges. You can see that there's a large variety and variability. So when we are looking at how to utilize these measuring resistivity and how to utilize that effectively, what we really want is to have a condition where we are trying to identify between a low resistivity material and a very high resistivity material in order to give us a good signal. And we do get that within basement rocks because you have your crystalline rock, which is a very high resistivity, which is then overlain by the weathered area, which will have water content in it, as well as be comprising sands and clays. So you can see how, my apologies, you can see how if we've got in a basement rock setting where we might have crystalline rock that might have very high resistivity indeed, which is also overlying it got clays and saturated sands, you can see that contrast is something that we can pick up within a 1D survey to support a field investigation work. So as we talked about already, but I'll go through again because what we're really doing with a 1D resistivity survey is we are passing a current across two outer electrodes and measuring the voltage change, the voltage within the two inner electrodes in order to calculate through a formula an apparent resistivity measured in ohms per meter. And the way, and as we change either the position of these or the distance of these, we then get either deeper measurements or a lateral change in the measurement. It's also good to know that we are looking at approximations and averages. So although we are measuring, for example, in this particular case, what we think is we're trying to get some readings for a point below the middle of this array. Actually, the signal that's being received in order to get this measurement at the point below the array is actually coming from a much larger area around the electrodes. So it is an average of a larger area of ground. Depending on the array, there's different types of array that you can use, and depending on the array will depend on where the shape of that will depend on where the main average of the measurement that you're picking up here is coming from. It's a bit easier to describe here. So there's three different arrays that's generally used. There's the Venner array, where the electrodes are all separated out at an equal distance. So A here, the distance between this electrode and the inner electrode here, the P voltage electrode, is distance A, and that's the same going across the entire array of those four electrodes. The Schlumberger array will have a smaller distance between the inner electrodes and then greater distances on the outer electrodes. And then within the dipole-dipole array, you'll actually be passing your current across two electrodes in one location, and then picking up the voltage from that current in another location, where the distance between the two will be between this distance A that you separated your current and voltage electrodes from to 5A. So this image is quite useful to see where we're actually getting the signal from in these different arrays. So you can see that the Venner array is getting quite a wide. It's taking an average from quite a lateral extensive area, but it's a slightly shallower depth, and so you're getting more of an average potentially at a shallower slightly depth. So when there's changes to in the heterogeneity of the ground laterally, then this will become this will take on those averages as well. Whilst in a Schlumberger array, the key signals being recorded is deeper but more laterally less extensive. So it's giving you more of an information about the depth just below the center of the array. And then the dipole is getting its averages from two locations rather than the center of the array, more either side. So depending on the configuration of your electrode will depend on the depth penetration that gets it. That you could say is the most contributing depth for that particular array. With a Venner array, the median depth of investigation is around 0.2 distance between A and B. And I apologize, I said 0.2 to 0.48 a while ago, but it's 0.1 to 0.3. So in the Venner array, your medium depth of investigation is looking at 0.2 the distance between A and B. So if this is 100 meters between this point and this point, then you're looking at your medium depth being 20 meters below the center of the array as a general average, with a maximum effective depth of being 40 meters if it was a 100-meter array, or 40 0.4 your A and B distance. With a Schlumberger array, it's just slightly greater, with your median depth being 0.19 AB and your maximum effective depth of investigation being 0.42. If the depth of investigation is also very much dependent on the geology. So this is an approximate number, but if the resistivity increases rapidly with depth, then your depth of measurement is going to be potentially slightly greater. No, sorry, more less. But if the resistivity decreases with depth, then you might get a greater penetration depth with your currents. I'm looking at a conceptual model here of a crystalline sort of basement rock setting, and you can see that within this conceptual model, you have some weathering in this particular location here, with much less weathering either side of it. So if you were going to be doing a profile across here, then what you would find is that you would have higher resistivity measurements, because remember you're taking a sort of average within a particular, depending on your spacing of your electrode. If your spacing of your electrode is giving you a depth penetration of, let's say, if you've got 100 meters spread, and that you're therefore going about 20 meters down into this material, and there's no scale here, but let's pretend that's about 20 meters, then you'll be getting an average resistivity measurement taking into account the material around this the 20-meter mark, and it'll be higher there than when you get to here, where you're going to be having much more less resistive materials, and that you can see that would actually then impact if you're profiling along with a constant separation traverse, how you'll have higher resistivities here, and then they'll reduce and then drop down at this point before then increasing again as you go back into the hard rock if you're moving your profile along from A to B. And obviously, when we look at groundwater and basement rocks, which is one of the main, most effective ways of using electrical resistivity, because of this contrast in resistivity between the basement rock and the weathered rock, then by finding areas where we have deeper weathering and higher water tables, we're going to have much greater success of water. So the approach when looking at trying to locate a well in this kind of environment is to, first of all, traverse, do a constant separation traverse in order to try and locate the zones of deeper weathering in a particular in an area that you think is of interest, i.e., in an area where you think a structure is passing along past your point, or even if you aren't able to do, if you've not got any information on structures passing your point, you would still want to do let's say the example used earlier, where there's I think you said it's a hospital about 300 meters land area around. You would want to do a constant separation traverse across the perimeters of that land to see if there's any points in that traverses where there is a deeper zone of weathering, i.e. you're looking to try and pick up areas where there's where your resistivity along that constant separation traverse is reduced. So in this particular diagram here, it's in this conceptual model, you have a fracture zone here with a slightly deeper zone of weathering. You would then come along with your constant separation traverse, which is where you'd have your electrodes all separated at an equal distance at a uniform distance. It doesn't necessarily need to be using a Venner array. You could be using a Schlumberger array as well, but you wouldn't change the distance between the electrodes, and you'd move that whole array laterally along. And as you're doing that, you're picking up resistivity readings, which over at this point are quite high at 300 ohms per meter. But when you're going past this point and you're reaching this zone of deeper weathering, the resistivity of the signal that you're getting back is reduced, and then it's going back up again as you've gone past that deeper weathering zone, and you're getting a more average signal from the, I mean, in this case it's limestone, but it could be crystalline rock as well. So when you're looking then to potentially do a vertical electrical sounding to get more information about the depth profile, you'd of course be choosing this point here where there's lower resistivity encountered.
Can we go back
Yeah,
just to understand it better?
sure.
So then I guess the separation that you would put within your electrodes, it will be also based upon how do you think that weathering area is. Am I right? To say, oh, okay, I'm looking more or less at 30 meters or at 80 meters.
That's
For
exactly
doing the
right.
traverse,
Yeah,
yeah?
that's exactly right. And I will talk about that in a bit as well. But yeah, absolutely. So if you're doing the survey yourself, then to get a to be able to decide on the initial distances, yeah, that you want for your electrodes to do that traverse, you would probably initially do a vertical electrical sounding anyway. Ideally next to a nearby borehole that you have a geological record for, so that it can you can help to calibrate your readings based on that. But if there was no boreholes around, you would do a vertical electrical sounding to start to understand what depth you get to when you encounter the vertical electrical sounding will give you an idea, an approximation of the depth of the crystalline rock in that, or the harder rock at that particular point in time. And then you would use that to then decide on your distant separations to then do the traverse.
Just mute. Okay.
But yeah.
Okay.
Or you would use something like this. So you would get it. You'd have a borehole records in the area. I mean, you would still do the vertical electrical sounding, but you could also use this as a way of configuring. You could say, okay, I know in my borehole records that weathering zone in this area is around 30 meters. Therefore, to investigate that, I need to have a separation of
100 meters
100 meters,
17,
exactly.
so
More or less 100 meters, you know, to get to that kind of, yeah, that depth.
Independent on the distance of the center ones, the MN.
So
independent of this, yeah.
Yeah, to do the so to get to the medium depth with 30 meters, you would go. What's that going to be? It's going to be more or less 150 meters, isn't it? Actually, to get to have a 30 meters as your medium depth, you need 150 meters traverse based on this kind of configuration.
And you just divide that into 4 to put the other n in the center, so they are all equally spaced.
Yeah, yeah.
It's key.
Here's a couple of examples of, so as you're doing the constant separation traverse, you can literally plot the readings encountered there and then on your computer, or even on a piece of graph paper, in order to decide on where you might want to do a vertical electrical sounding. And so taking into account this kind of picture, in this particular case, this traverse has been going along. It's reached a maximum, a minimum, as it were, resistivity here at this point, and then the resistivity is increasing again. So you would consider doing a vertical electrical sounding at this point. And similarly, this is the low point for this traverse, and so the vertical electrical sounding would be carried out here. I've got other examples very similar. So this is a different survey carried out, which is in the literature, and you can see that they're putting their vertical electrical soundings at the low points within their constant separation traverses. And then here's an example from Yumbe refugee camp, where this is where the borehole was ultimately drilled in this traverse, and that was successful. And then this is from a couple of examples that you shared, Maite, earlier, from your own investigations that have been carried out. So this is from a UNHCR report. You can see that they carried out a constant separation traverse and then decided to do soundings at these low points within that constant separation traverse, and likewise here. And then another report that was shared with me for the Rocken Hospital. 2 traverses were carried out either side of the hospital. These are the profiles that were carried out, and then they chose their vertical electrical sounding positions based on that. I mean, admittedly, they didn't have very much to go. They didn't have very much to go along there. Yeah, but you can see what they were trying to do. Actually, this could have been a mistake because this was an interesting feature in this particular constant separation traverse. It looks to me either it was a mistake, and if it was just a one-off reading, you might want to do the reading again. But if there was a couple of readings up here or going up and down this profile, then that might be showing a dike crossing the area with a higher resistivity, in which case, actually, a borehole drilled right next to the dike might have been a better option in this particular case. I saw a hand had gone up. Has anyone got a question?
There's 2 questions.
Yes, it's a question. Please, can you go back to the previous slide?
Yeah.
Yeah.
Back to here.
No, not that one. Just not this one. Again. Yes, this one. This diagram. So my question is related to this diagram, just to understand how you interpret this lower point according to the shape. Like the first diagram, you see that this lower point is more like narrow or sharp. Then for the second diagram, you see that it's more like a constant down at the bottom. So for these 2 options, did that mean something like what interpretation can you come out with this one for these 2 options?
Yeah. So I would say that this is a better signal. The lower one is a better signal than these ones. One of the sort of rules of thumb is that these sort of troughs, as it were, that are being picked up within the constant separation traverse, if it's just one point at the base of the trough, it's not necessarily giving, well, there's less confidence in that as a signal compared to where you have more than one point at the base of the trough in this particular case. So that's a sort of rule of thumb. But of course, we are because of because of actually what's happening with the readings, because we're averaging over a larger area, and there might be lateral variability over here, or there's many things this is it's a crude tool, basically. So although I would say that this signal is better than this one because of that, who knows, until you drill it, who would actually really know. But a rule of thumb is that if you only have a single signal at the base of a trough, then that's less of a good signal than something with multiple points. Does that? Yeah. So I can't. Ultimately, we're working on averages here the whole time.
And there is Aurora as well.
Yes, just to know about the horizontal axis, is what exactly? It is the distance between A and, yeah. The horizontal axis of the graphic.
Yeah, so this distance is here, 0, 2, 4, 6, 8, 10, 12. This is actually a distance along the transect. So you would start at 0 meters here, and then you'd move the whole array 10 meters along, perhaps. Or 5 meters along, depending on how many readings you wanted. 20 meters along. So you'd move it a set distance along, and then you take another reading. Then you move it a set distance along and take another reading. So they haven't got distances here, they've got station numbers, but in this particular case, they've also got station numbers, but you might, instead of having a station number, you might have a distance. So you can see why they've got these. This is that what first reading, second reading, third reading, fourth reading. So that's where they're getting this numbers from. It's just the numbers along the profile, but the distance between each reading isn't clarified on this graph. But it might be 5 meters or 10 meters nominally.
Okay, but is this distance AB, no? The total distance?
No, this is, so with a constant separation traverse, whether you're using a Venner array or a Schlumberger array, it doesn't really matter. You can do a constant separation traverse with either, or you could use a dipole array too. But what you're doing is that you're keeping the electrodes all at the same distance. So you've decided on the depth of investigation. You're keeping the electrodes all at the same distance, and then you're moving the entire array laterally along by 5, 10, 15, 20 meters. So that's where we're getting these profiles from. These are all the electrode configuration is the same. It's just being moved laterally along a line.
Okay, that's clear now. Thank you.
And then one other question, sorry. Like if you expect, I imagine you always try to go perpendicular to the features that you're thinking to try to find with your array. Am I right?
Absolutely, yeah. So if you've got a structure that if you've mapped out structures, let's say this wadi may well be running along parallel to sort of a more regional structure system, maybe, then yeah, you would be, so what they've done here makes perfect sense. If the structures are running this way, for them to then run their lines, run their profiles perpendicular to where they think the structure's running, so that they can pick it up. However, if they've been if actually they did, I mean, there isn't, in this particular report, there wasn't any structural analysis done, but if they'd looked at topography and looked at a regional geology map and seen that structures were running this way, north to south, then they might have decided, actually, we should have done one more profile across here to see if we could pick anything up interesting, structurally, that might be running across here that these lines might miss or might not pick up very well. So yeah, and I mean, probably they should have done one. I mean, it's good practice to do constant separation traverses. This was good. This was good practice, but then it would have been good practice also to do one across here and perhaps one next to the wadi as well, on a perpendicular to these two lines, in order to see if they could pick anything else up that these lines weren't picking up. But yeah, you would design to try and cross structure perpendicular. Any other questions, or I'll move on to vertical electrical soundings. We will come back to this, don't worry. We're going to be coming back to this again. So the difference between that constant separation traverses and the vertical electrical sounding is that instead of trying to see the lateral variation in resistivity with the constant separation traverse, with the vertical electrical sounding, we're just looking to get a depth sounding in effect. So we're looking to see what the horizontal changes might be to resistivity. And so to do that, what's done is we normally a Schlumberger array is used for this kind of VES measurement. Oh, and you are keeping your central point the same, and then you're slowly expanding out both your A and B electrodes, which are passing through the current, and your M and N electrodes, which are measuring the voltage difference. So you're slowly expanding those out. So you can see in this diagram that, you know, when the electrodes were close together, they were measuring a smaller average resistivity with a certain depth, and as you expand it out, they're picking up and taking on within that average greater depth. So as the electrodes have moved further and further apart, we're getting progressively deeper into the earth to measure the resistivity properties of that deeper layers. There are certain rules, mathematical rules, associated with the distance between M and N compared to the distance between A and B. And these are summarized through this formula, where the inner electrodes are kept as fixed distance as long as the distance AB divided by 2 is divided by 30 is less than the M and N distance, and likewise AB divided by 2 divided by 3 is greater than the M and N distance. So that's the important rule to remember when doing a vertical electrical sounding, in terms of these distances, the M and N compared to the A and B. So what you see normally, and we will see it in some examples in a few minutes, is that as the A and B electrodes are expanded out, then at certain distances we then expand out the M and N electrode as well. And in order to make sure that we keep continuity of the measurement, then we will, for example, we expanded out the AB from 5 meters to 10 meters, and then from 10 meters to 20 meters. Then we want to change the M and N distance from 1 meter to 2 meters, let's say. Then we will take another measurement where the A and B are back. We'll take a measurement at 20 meters A and B spacing with the M and N being at 1 meter, but we'll take another measurement with the A and B at 20 meters with the M and N at 2 meters. So we have a repetition of a measurement with the A and B spacing in order to smooth over the changes that we have with the M and N. And you'll see I'm explaining that now, and I don't. But we'll be going through this when we look at actually data analysis and data interpretation, and you'll see a little bit more about why that's important to have a repeat of a measurement in order to help with the interpretation of the data afterwards. Horizontal layers should give smooth sounding curves. So if you see data where vertical electrical soundings where the data is going like this, it's very likely that the data is of poor quality. What we do want to see is smooth curves being produced by the data because of this rule of averages. By increasing the electrode size, distance, we might be reaching areas which have higher resistivity, but it's not going to be an immediate sharp thing. It's going to be, you're still going to be taking measurement from the area you just measured, and you're going to be adding to that with some resistivity from the deeper area that you now encountered. So you should see a smooth transition between one resistivity layer and another within the curve. So that's something to very much bear in mind when looking at other companies' reports and their data sets. So when you're interpreting a sounding that's collected, you can interpret it through using through the curve itself with a 1D interpretation, or you can combine different vertical electrical soundings together to create a 2D section, similar to the ERT section that I showed you in the previous session. There's different ways to interpret a sounding, a 1D sounding. Historically, people used master curves, but of course now it's all about software, computer modeling and software. And we're going to be using a very simple software that's effective in the practical after the next break. So this is an example of a resistivity curve, a vertical electrical sounding curve, where you've got electrode spacing at the bottom, and you've got the apparent resistivity that's being measured running along the x-axis, sorry, y-axis. And in this particular case, you had an initial resistivity measurement of around about 10, 20, 30, 40, 50, 70 ohms per meter, which ultimately transitioned into a resistivity measurement of about 350, 400 ohms per meter. And it's a two-layered system. So you can see that although the actual boundary between that two layers would have been sharp, the resistivity signal collected over different spacings was smooth. Yeah. In this particular case, we have a three-layered system where we have an initial resistivity for the top layer that's around about 100 ohms. The curve is starting to reduce down, and if we didn't have a third layer, you'd expect it to in the end stabilize and flatten off again at the resistivity value of the bottom layer. But actually, at a certain depth, we then interact with a third layer and the curve changes again. And so we have this kind of shape. And these three-layer systems can be shaped in different ways. Here we had going from low to high to low. This is quite a subtle where it almost looks like a two-layer system. And then the C curve here. This is actually a classic shape that we would be looking for within a crystalline basement rock setting, where you have an unsaturated top zone that might have slightly higher resistivity, going into a saturated weathered zone which will have lower resistivity before it encounters the crystalline basement rock, and then the curve goes up. And this curve might keep going up and up because the resistivity of the hard rock could be in the tens of thousands. So it's these kind of curves that we'd be looking for to help us to determine the depth to weathering within a crystalline basement weathered setting, where we can sort of suggest a three-layered model of unsaturated, slightly more resistive, saturated, weathered, and then crystalline rock. Yeah, and it's just this is a slide describing different types of shapes and how they're called. So I was just talking about a bowl curve then when I was talking about water supply for a crystalline rock. You can have different types of curves too. We're going to go after break to look at how we would actually use IP2Win to taking vertical electrical sounding data and how we would then create our own interpretation of that data. We talked a little bit already about resistivity values for different types of geology, but just looking more at the crystalline basement rock setting now, black cotton soils might have a resistivity of, I mean, this is a particular value obtained for as one example, but you know, in that kind of range. Then you're going into your laterites and clays unsaturated with these sort of higher resistivities, and then we're going into this into the saturated area. There's the static water level here. So we're in saturated now as sands and potentially clays still, and you can see that much more lower resistivity now. And when we get to our aquifer system, and then when it goes into the crystalline rock, the resistivity massively starts to increase, and as the fractures and things dry out and the rock becomes more competent, this will just only increase. Yeah, and I think I've just been running through that. Actually, you can see here's a curve for crystalline rock, and in this particular paper, this author specifies that for a successful drilled well in Zimbabwe, the thickness of the saturated overburden has to have a resistivity of between 30 and 150 ohms and must exceed 25 meters. So they're looking for they're looking for this layer here to be at least 25 meters deep, with a resistivity of between 30 and 150 meters ohms to make it to have a success drilling a borehole.
So one question, sorry.
Yeah.
In the previous graph that you have this, I mean, you have the curve that you are measuring as you are expanding, and then I guess the other line, the square one, is the one trying to draw the thickness of the layers, or?
Yeah, no, don't worry about that just for a second, but we will
Okay.
get to, but in the programs you'll see that this is how they, yeah, it's a sort of program, it's a computer tool. It's got nothing to do with the curve, but we'll that same sort of way of an analysis is used in IP2 Win. So we'll be using that ourselves. But yeah, it's not the data at all. Yeah. So there's some important limitations and uncertainties that it's also useful to be aware of when looking at 1D resistivity data and vertical electrical sounding specifically. And because of these things, it's impossible for anybody to give 100% guarantee for a productive borehole based on geophysics. It's just a way of improving odds. So I'll run through each of these in turn just to give you an idea about why everything is uncertain. So vertical electrical soundings assume that vertical layers are homogeneous, that you will have exactly 20 meters, let's say, of sand, which is completely homogeneous running across the entire profile. But of course, that's mostly not the case. So there's misinterpretation as changes in the horizontal profile as you expand out the electrodes cause impacts on the reading that you're trying to get for the depth. And that might result in blips within your data set like this, which it doesn't make any sense if you're thinking about depth, but it's because you've actually expanded your electrodes outwards, and now they're encountering other different geologies laterally as well. So this is an example of that. Where the signal is in this particular paper, the interpretations of the 1D sounding are have significant differences that reflect the lateral variations in the geology. So this is where this is the same point in terms of a vertical electrical sounding, but what they've done is they've done the vertical electrical sounding from east to west across that point, and then they've changed they've then done the same sounding at the same location, but instead they've been expanding their electrode out north to south. So in the east to west direction, they get this curve, which is telling them about their the geology of what they think is the depth of geology. But then in the other direction, at exactly the same point, they're getting this curve. So you can see how that lateral variation can have considerable impact on the vertical electrical sounding. Does that make sense?
And that was with horizontal layers, that normally they were homogeneous horizontal layers.
I don't know the exact detail of this particular paper, but the point is that I'm just trying to think of here. So let's say they did this vertical electrical sounding here. In that paper, what they did is they did in one vertical electrical sounding, they extended their electrodes out to north and south, and then in the second time they did the vertical electrical sounding, they extended their electrodes out east to west. The central point for that vertical electrical sounding was exactly the same, but the curve they got is very different because the geology laterally is changed a lot.
Yeah. So in a way, even though, I mean, you are basically, your point I mean, the measurement, you are going to put it under that specific location where your thermometer is located, right? And now because you are mixing different heterogeneities, as you are saying, from the soil, you just get different readings, but then you still have to remove those heterogeneities for knowing which exactly you are dealing with. I mean, I'm getting, yeah.
I suppose my key point is that whatever data you get is not going to be exactly, it's not going to give you, you got to bear in mind,
yeah,
you've got to bear in mind that you're taking averages based on how you put your electrodes in any particular area, and it's also taking into account lateral variety as well as depth. And it's something to bear in mind, but it doesn't stop the usefulness of doing a vertical electrical sounding. It just can, it means that your vertical electrical sounding is not necessarily going to be exactly accurate. There's another issue with vertical electrical soundings.
I think there's another question. Let me see.
Oh, okay.
Yes, I just wanted to know, like practically on the field, how to know the right direction on which we are going to put the electrode, because what I usually see on the field, the company, they usually use kind of baguettes, saying that those baguette is like to localize the fracture. And Maite was saying when they localize this fracture, they will now put the electrode and move it perpendicularly. But during the beginning of your presentation, you were saying this method of localizing fracture is localizing fracture at less than 40 meters. So I really want to know what is the best method to localize this fracture on the field. Thank you.
I'm jumping a little bit ahead, but I think it answers your question, and I think it's probably good to address it now, and then we can go backwards. But I mean, Mighty said earlier on, it's better. She raised the point that if you've got a particular structure, in this case, these are the lineament directions, then you want to run your constant separation traverse. You'd want to run your constant separation traverse across these perpendicular to these lineaments. But then when it comes to the vertical electrical sounding, what they recommend is that it's good to perform these anomalies parallel to the lineament trend. So in this particular case, this was one constant separation traverse. This was another constant separation traverse, and they found this lineament here. Yep, running across here. And so once they'd found that lineament with these two constant separation traverses, they then carried out their vertical electrical sounding running parallel to what they thought the lineament's direction was, in order to pick up better the actual lineament, rather than to be taking the rather than to take a lot of the measurement away from the lineament. Does that make sense? So you would do a constant separation traverse, try and pick up a fracture system, and then you'd run your vertical electrical sounding in this parallel to what you think is the direction of that structure. Is that the question? If I get that right?
Yes, that's the question. But usually we are doing the opposite on the field. We do it perpendicularly to the fracture, not like parallel.
Well, that's not what's recommended, at least according to this paper. I personally quite like what this person's done, in the sense that they've done a sounding both ways. But obviously that's not always practical when you're looking at in the field conditions. You might have to do the vertical electrical sounding one particular way based on the easiest, the road direction, whatever it might be.
So just let me just try to repeat what you just said, just to see if I understand it. So basically, in the other picture that you put, could you put it back again with these alignments? Then you take your constant separation probes, and then you go in these both arrows that are like this.
Yeah.
And then basically, as you are measuring, you have one of these dips in this anomaly of parallel profile. And then you say, okay, here I have something below. And then you do the second one, and you also find another dip into your profile, right? And
Yeah.
then you assume there might be something like a crack or something below that crosses in
You believe
perpendicular mostly. Yeah.
Yeah, you're hoping to pick up this lineament, but you might have planned it out to try and pick it up. You then pick it out, and and sorry, I interrupted. Yeah.
No. And then then is when you start expanding your electrodes in order to now go more in depth and lateral about what this lineament looks like. Right?
Yeah,
Sort of.
exactly. And
Okay.
it's recommended that you would expand your electrodes out along in
That line.
in parallel to the strike of the lineament. Yeah.
Okay, thank you. Just
Yeah. So we talked a little bit about the lateral variation. Next thing is the equivalence, which is really stating that if this, because of the way that you're measuring resistivity in the ground, if you've got, for example, in this example, you've got a 3-layered system where the layer 2 has much lower resistivity than the layer above it. The point here is that the thickness of P2 here could be half the distance and double the resistivity. Sorry, half the resistivity, or it could be double the thickness. I'm getting myself a bit muddled up here. Sorry. Basically, what this is saying is that if this is double the resistance, then the layer could be half the thickness and still have the same kind of signal in terms of resistivity as if the layer was double the thickness and half the resistance. Does that make sense? Because it's just mathematically resulting in the having the same effect on the way that the current can pass through the ground. Because if you've got, so current's always traveling through the easiest pathways. So if this is more, if you've got if you can imagine it a bit like a pipe, if you've got a pipe that's more conductive, then if that pipe is small and has double the conductivity, it will enable the electricity to pass through at the same ease as if you've got half the resistance. Like it's more difficult to pass through, but it's double the thickness. Does that make sense? So you can't pick that when you take your measurements at the surface without knowing the thicknesses of these layers. You can interpret the data as being half the depth, double the conductivity, or twice the depth at half the conductivity.
I guess from there, the very important to really know which layers you are going to find to more or less take out that information, right? To pick up whatever you are looking for. Because, I mean, yeah.
It's just another unknown, unfortunately, unless you've got good borehole records for the area. It's a bit of an unknown as to what's. So this is where your conceptual model becomes really important, and in order to know what you but you if you had a borehole record for this area, then you could start to set, or if you knew what the resistance was of a particular layer that you were expecting to encounter, then that can help you then with the analysis of the data afterwards. But yeah, that's the rule of equivalence. So in a basement rock setting, where the water saturated aquifer has a lower resistivity than both the overlying unsaturated weather material and the underlying fractured bedrock, we have this challenge where of equivalence. So it is something to keep in mind, but and perhaps we can explore that a little bit more with when we do our practical later on. This is a curve showing how you could have these how the actual theoretical curve would look like based on all four of these scenarios, and how similar the curves are actually looking based on 1, 2, and 3 specifically. And then the final issue to consider is that of suppression. And suppression is a problem encountered where a second layer has a resistivity that's halfway between the top layer and the bottom layer, so it kind of just disappears in your curve. So or is suppressed. So in this particular case, if this layer didn't exist, the curve would look very similar to if the layer does exist, because it just gets suppressed by the low to high that you already have going, if that makes sense. So that's the final issue, which where you just might have a layer, you might have a different layer that you'd want to pick up that you just can't seem to locate within your curve, because it's suppressed by the lower and the upper change in resistivity. And here's another example of how that suppression just doesn't, you can't see it in the geological curve, and they've added it based on their understanding. Other issues also might include where 1D interpretation would be very difficult, as if there's a lot of if there's been faulting in the area and excessive dips of the subsurface along the survey line, estimated more than about 15%, then that's considered very difficult then to actually be able to get any kind of a good result with a vertical electrical sounding, because the trouble is that the lateral and depth, the lateral changes in the averages as you're trying to do this are increasing because of the dip of the structure. Any questions on any of those points, the challenges associated with vertical electrical soundings? It's not to put off from the usefulness of a vertical electrical sounding, but it's just to be aware that it's not cut and dry. The measurement that you take on the ground, at the ground surface, it's not cut and dry that what you're recording is actually what's happening below the ground. It's just something to be aware of, And of course, it shows the importance of trying to get as much other information as possible from existing borehole records and things, so that you have a fair idea about what you should be expecting within that, your conceptual idea, before interpreting data. Any, was that clear enough? Or any need for more explanation? Sorry, I can't see if I think, but
No,
I'll
I think
carry on.
people are putting thumbs up. Yes, yes.
Yeah,
yes,
good,
okay.
good.
I mean, just one little thing. Sorry for the very last one is that if your layers are inclined more than 15 degrees, means that then it would not be, I mean, good to use.
Yeah,
sets.
it starts to become difficult to get a good
interpretation, a good
yeah,
outcome from it.
exactly.
Okay.
Yeah. So we've talked a little bit about what equipment is required to do a 1D survey. Oh, yeah. Aurora, I can see your hand's gone up.
No, it's just a comment that it's a bit disappointing, all these things that you are saying, and yes, as you are saying, if we need to complement with other information as existing boreholes. But I was especially surprised with the orthogonal one, because it's very different, the profile that gives. So yeah.
The which one?
This study that do the comparison between the orthogonal direction.
This one.
Yes.
Yeah. No, I mean, I think it's a very good example of the sort of the variability of the subsurface, both laterally and at depth, and how that does impact on any reading. If you're trying to understand depth, it's going to be influenced by the lateral variability as well. And yeah, I think it gives a good example of the uncertainty associated with using geophysical methods in general. But not to say that they're still not useful. The equipment needs for carrying out 1D electrical resistivity surveys, I think you need your thermometer, you need your batteries, you need your 4 cables, at least 6 electrodes actually. I mean, you only need 4 for the actual measurement, but if you're going to be carrying out constant separation, traversing, or vertical electrical soundings, in order to speed up the process of taking the measurements, you want a lot more electrodes than the 4. Surveyor tape to measure the distances between electrodes, a GPS to obviously get all your coordinate points where you're taking your measurements from, hammers to hammer in the stakes, the electrodes. The electrodes themselves can be quite long. We're going to talk a bit about challenges in a second, but getting enough contact with the ground surface to enable measurements to be taken is very important for electrical resistivity surveys. And then various tools for measuring a current, mole grips for getting electrodes out of the ground, pliers and other electrical equipment to fix wires and things like that, and fix connections. Water is very useful to support the connection of the electrodes to the ground, and salty water obviously is even better at improving connection. And radios, because often if you're 100 meters away from each other as you're carrying out a survey, then having a radio system makes life a lot easier. Other contractors use whistles and things like that to communicate. Quite a lot of this we'll cover, but I'll run through it again just for repetition's sake. So obviously the DEST study itself provides information on the geology, the hydrogeology, borehole data, and potential lineaments that you're going to be targeting for the geophysical investigation. Your profiles, your constant separation traverses, are then carried out perpendicular to those major lineaments marked during your desk study. Profiling can be undertaken using station intervals of 10 meters. So that means that you're moving your electrical array every 10 meters. It can be less than this or greater than this, but 10 meters is probably a good standard rule of thumb to pick out anomalies in a fractured setting. When significant anomalies are recorded, you could profile again at those anomalies at shorter distances to see if you can pick them up again different. So you could run 2 or 3 profiles at, parallel to each other to try and keep picking that anomaly up at that place that you've picked it up from. In the center of the most significant anomalies, you'll do your vertical electrical soundings. The sounding is extended until sufficient data is available to define a 45-degree slope, indicating that you've reached bedrock. That's this slope I'm talking about here for a crystalline basement rock setting. So you want to do a sounding until you reach your crystalline basement rock setting. And then based on the different vertical electrical soundings you carried out, you would choose the most appropriate one, which has the deepest saturated thickness of weathering, basically, for your drilling target. So when you're planning your, a few tips here, when you're planning out to carry out a survey, obviously a profile, you obviously want to make it as easy as possible for yourself to carry it out in order to speed up the works and to not interfere and upset other people. So going along pathways that are quite straight and perpendicular to the structures that you want to pick up close to where you want to drill a borehole is obviously most appropriate. And access for drill rigs, you obviously don't want to be doing profiles miles away where you're not going to be able to get a drill rig. Getting electrical contact to the ground is very important, and so using long metal stakes as your electrodes, ideally made of copper or stainless steel, perhaps up to 3 feet length, is good. If contacts are a problem, then you'd pour salty water around the electrodes to improve the contact. With the terameter equipment, you stack measurements, i.e. you'd ask the terameter to take up to 16 consecutive measurements of that same electrode spacing. Now, that's called stacking. So it takes many measurements, and then it makes sure that the measurements are similar. If you have to stack more than between 6 to 8 times, then the chances are that you're not getting a good contact with the ground, that the data's no good somehow. So you would need to relook at that electrodes and look at doing that measurement again, because you should be able to get a good average measurement within about, well, by the time you've taken that measurement 6 times. Write down all the data that you collect, as well as recording on the machine. And when you're carrying out the constant separation traverses, you should be basically analyzing the data there and then, so that you can then go straight onwards to do the vertical electrical soundings in areas that's of interest. We've gone through this diagram, so I'll jump over that now. This is sort of touching a little bit on a question that asked earlier, but here this was produced by We Consult in Uganda, but it's a very useful table for providing a little bit of a scoring system about how to grade anomalies found in constant separation traverses. So they're saying if the topography of the location is determined for the groundwater, if you're in a valley or a lower foot slope, then the likelihood of getting water is higher than if you're at the top of a hill. If the lineaments from aerial photographs or topographic maps are very clear, then you're going to be much more likely to get water than if you can't find any lineaments. The anomalies that you record, depending on the shape of the anomaly, will with the background readings. So I'm going to have to probably go back to this to explain that in a bit more detail. But depending on this anomaly here, depending on the shape and depth of this anomaly compared to the background readings, which is away from the anomaly, that's probably a bad example. But for example, here, these shapes of these anomalies will depend on the success of the borehole as well. So, for example, if the contrast between the shoulder and the lowest anomaly is less than 1.5 or greater than 4, then it's not likely to be a very useful anomaly. But if it's between 2 and 4, then it's probably of interest. Does that make sense? That's the contrast between this anomaly here and the background. So in this particular case, it's reading a resistivity of 6 ohms per meter here compared to a background of about 10. So that's almost getting to be about twice a contrast, which is therefore reaching into this scoring system. But if it was less of a contrast, then you wouldn't be so interested in it. If it's got good shape, the anomaly's got good shape and value, then you give it an 8. If there's no shape, like the one that we saw here in the example at that hospital here, then we're not going to give that anomaly very much credence as a good place for doing a vertical electrical sounding. And then when you carry out your vertical electrical sounding on the anomaly, the aspects of your VES dip, this is the dip that you're getting here. This is this saddle, as it were, in your reading. Oh, my apologies. If that dip is greater, has a resistivity greater than 200 ohms, then it's not of interest, because you're looking for saturated weathered material. If it's between 10 and 100, then it's of really useful interest. And also if the actual resistivity data that you're receiving is similar to the anomaly that you picked up with the constant separation traversing, then that would give you more score than if it's not. So those are some very useful sort of tips from We Consult that help to give you, when you're looking at these anomalies and then the shape of the curves associated with the vertical electrical soundings, how to get a bit more credence onto judging the value of the both the anomalies in the constant separation traversing, but also the shapes of the curves from the vertical electrical sounding. Take a look at that, perhaps again later on once we've done the practical as well, because I think it's for me, I found that a very useful reference table over time. Any questions on that have come up since regarding how to carry out 1D surveying? Do you have a better picture now about the sort of the way you would go about doing it? So you first start with the constant separation traversing, you find anomalies within that, and then you carry out your vertical electrical sounding, and based on the shape of the curves that come out of the vertical electrical sounding, and we're going to do the interpretation of that after the break and have some examples to see for ourselves based on the shape and then the depth of the shape in terms of the resistivity of this and the depth of the saturated material will then give an indication as to how successful a borehole is going to be when you drill it at that location.
Sebastian has the hand up. Sebastian.
Yes, I have two questions. The first one you can answer very, very fast. Is about linearment. So if you have a linearment in between granite, like a vertical linearment, three questions. When we talk about linearment, it's more or less vertical or oblique, no? Or not?
Yeah,
Can be horizontal.
It can be 60 degrees, 30 degrees. They vary. Yeah, it depends on the faulting that happens.
Okay. So if we have a linearment between a granite and a black cotton soil, do we consider is very good as shown in the tab, like if you have a linearment very clear, but between very bad, let's say, very bad soil for water, like could be granite and black cotton soil. Like you will not find water in this linearment, no?
Yeah, there can be. So we're kind of going into that sort of in that previous presentation where we were looking at, for example, the schist, where so some lineaments can be absolutely clay filled and be dry and no use at all for water supply. This isn't a very good image, to be frank, but it's so. Yeah, it's not easy to tell, and so the way that we would look at perhaps before going in to do a geophysical survey, I'd be keen to understand the structure, the geology itself, and then looking at the different history of the structures. So there might be some fractures that are more recent that are water bearing compared to older fractures that have been closed up or whatever as well, depending on their strike direction. In particular geologies, that you've certain structures might not be like the example about the schists. Although you might have a deep weathered zone that might be clay filled and it might not be suitable for water supply as a target. So you might have to think about something else for a target. So yeah, it isn't, you can't rely on you have to understand the geology in order to then decide on what type of signal you're going to get. I mean, it's just the same with 2D electrical resistivity tomography. Sometimes the most resistive material, i.e. the basement, is not the target, and you're looking for the most conductive. But it can be exactly the opposite. Sometimes you're looking for the most resistant material because it's got the sands in there, compared to the more conductive material, which is the clays. So you have to know the geology in order to make your interpretation.
Okay, it was a bit longer than. Can I go for the second question, or maybe I let Laura first? Okay, so my second question is about this equivalence diagram you show, depending on like a sandwich layer where the middle one is has different widths.
Yeah.
You see this? Yeah, this one. So when I see the curve 1, 2, 3, 4, I don't understand. So if the good layer is the one in between two, is the middle one. So why in the curve 1 we identify the good layer with water so deep? I mean, it should be at 1 meter and a half. Like for the example number 1, I mean, we have good conductivity at 1 meter and a half, no? So why in the curve it's appearing
Mm.
so deep at 4 meter or something like that?
I didn't explain this very well, but I mean so what I suppose the key way to look at this is to think of it a bit like a pipe, really, actually. And I mean, in all four of these cases, we have the layer 1 having a resistivity of about 100 ohms per meter, and then the bottom layer as in the crystalline basement, let's say, has a very, very high resistivity. And so what this is trying to show is that when you're taking the sounding and trying to get these curves, the curve shapes can be quite similar despite the differences in the actual hydrogeology that you might encounter. And the reason being that when you've got a very conductive layer, i.e. its resistance is here 2.5 ohms per meter, you don't need a great thickness of that to enable the current to pass through. And it would be, it's mathematically, it's almost the same as saying that you've got, instead of I don't know what the thickness is of this, 0.5 meter thickness of a low resistive material, you actually have 4 meters of a slightly higher resistive material. It will have a similar signal coming out. So therefore in this particular type of scenario, it would be quite important to know what the kind of depth to basement rock is, in order to, when you're doing your analysis, to have a better idea about what you should be expecting. Does that help?
Yeah, thank you. Well, I don't understand why the low resistance point is so, at the end, so the low resistance point should be different, no? For each of the 4 example. This is why I want to understand. Yeah.
Well, I think the best way to start to understand this is to play around with
Okay.
the software. So
Yeah,
yeah.
it's good. Thank you.
I think there's also Laura.
Yeah. Thank you very much, Jerem, for all the explanations. I must acknowledge that I think I have a good way to go to be able to grasp everything that you've been sharing. My question was more on the, if I can say, practical terms. Like you were highlighting at the beginning that one of the problems we often have is managing contracts and the risk we often try to, the risk and the knowledge we often try to direct to the contractor, where we ask them to do the geophysical survey, to select the point, and then they just get the responsibility of all. With all with all that you've been sharing and the uncertainties that there are in the geophysical studies, what would you recommend for us to be managing better these contracts and the mitigating the possible risks that we find? I don't know if my question is clear.
No, it is.
Okay.
I think I'd fall back on asking. So there will be different contractors with different. There'll be better contractors and worse contractors at the end of the day, and there'll be some contractors that are more scientifically driven compared to other contractors just looking to make some money. So how to determine a better contractor from a worse contractor, one way would be to ask them before they actually, is to ask them how for a field plan stroke desk study prior to releasing the secondary part of the contract that would be then associated with carrying out the field work, and that might include drilling. So that's one way, is just to like sort of breaking the contract up into sort of, and I don't know what the practicalities of doing that would be, but to say, look, we want first of all your field plan and your desk study in order for your, we want to understand your conceptual understanding of the subsurface and have a field program in place for us to then approve to go forwards with the actual that field work. I think that would enable the contractor to have a bit more flexibility as well, because it would enable them to be able to understand a bit more about the site conditions before they put together a budget for doing the fieldwork element. So it might work on the contractor's favor too, in order that they have that bit of extra time preliminarily to understand what they're up against. The second point, I guess, is that if you as MSF are able to have a better, clearer picture of what should be done in the first place before you even get to the contracting stage, then at least your terms of reference that you then send out to contractors for quotation will help guide them to doing the right things to meet with the site conditions that you're trying to get over to get a water supply for whoever it might, for the hospital or for the beneficiaries. So that having more knowledge about what types of work should be done is going to help you then to get the right contracts ready for the contractors. Does that help? It's
yeah, I think that those 2 points are things that I would retain. And then what do you think about asking the same contractor that is going to do the drilling to also do the geophysical studies, and would they have the knowledge and the technical capacity to do it?
Yeah. So one rule so whether it's the same contractor or two different contractors, one nice thing to do is to make sure that the driller, the geophysicist, and this is difficult to actually arrange practically, but for the person who sited the well to be present when it's drilled is a useful learning curve for them, and also adds a bit of pressure to them to get it right, rather than saying X marks the spot and walking away. So if it can be arranged for the person who's siting the borehole to also be around for the drilling, then that's a good learning experience. I've got no real. There's a huge number of drillers who will be siting their own wells. I don't know how many. I would say that that's probably the majority of contracts are still got the driller siting their own well. So and I can understand the attraction of it when you're looking for it's quite a tempting thing to then be able to say, look, no water, no fee, and that the driller takes on all the risk. Certainly with people who've got set budgets, it's very difficult for them then to take risks on. But I mean, the ideal scenario would be to have a very flexible contract with the driller, and to invest in investigation, to spend time building up an understanding of the water resource before, and that might involve drilling, site investigation work, to build a better picture. But would involve then the contract that you then have to negotiate to say, look, we're taking away the risk from you in terms of no water, no fee. So we want a cheaper rate for drilling, please. We want it to be a bit more experimental. And so please charge by the meter or charge by the day rather than or have a charging approach that enables that experimentation, and then obviously bringing in the right having to invest a little bit more in terms of the surveying, etc., that you're then investing in as an organization to build up the idea of the water picture. I mean, that's the ideal. It's not the most it's not going to be, it's not the richness of the additional information that you obtain from that will work in the favor of longevity and long-term sustainability of water sources. But it's not, I can see why it's not, I mean, it's not very common to do that approach. The most common approach is simply to no water, no fee, get the borehole in as quickly as possible because we need the supply. But it's I'm meandering a little bit here on that question. I'm sorry.
It's fine. I think it's a difficult answer, and it's really challenging to bring it to practicalities, no? But thank you very much.
You want that we do a break now? So shall we break for like